Okay, so before the exams, we did a couple of lectures with reviews. So this is probably out of your mind after starting with 1 degree of freedom. But we started doing the 2 and multi-degree of freedom. But basically, we start with 2. Okay, so what does that mean? You're going to have 2 masses. All right, and we kind of study that we need to be able to find the equation of motion, but the steps about how to solve this problem will be identical to the ones we did for the 1 degree of freedom. All right, so over here we say, if we have the equation of motion here, what should the equation of motion be able to describe? It should be able to describe 2 different types of motions. One is that these 2 blocks, and 1 and 2 could be moving together to the right or together to the left, or the other type of motion would be what? Moving away from each other, no? Okay, so you see, step 1, what is always do some type of figure free body diagram. That's what we did. We did 1 for each one of those masses. Step 2, write down kinetic equation of summation of forces. What type of motion do we have here? Just translation. So just this equation should be sufficient, no? We do this, blah, blah, blah. And then obviously, since we have 2 degrees of freedom, you need 2 equations. These are the 2 equations, but I told you that it's going to be easier if you put everything into a matrix form. Okay? Now we say, okay, first let's do the free vibration, which would be the easiest case. And with the damping equal to 0, and we solve. So this reduces to this. Again, now that you have the equation of motion, what is the following step in order to find the solution? You assume the solution. Okay, so all the time the same process. You assume the solution, you substitute into these 2 equations, and you get this equation here, these equations here. Now, this needs to be equal to 0. Again, what is the procedure? When is this satisfied? When this is 0 or when this is 0, no? Okay, so anyway, so it's this one times this one, so this is the trivial solution. Or when the determinant of this is equal to 0, we get to this B quadratic equation, which will be lambda squared. This is known as the characteristic equation. You solve for the 2 roots of lambda squared. So maybe here I should have put lambda squared, here square. I think I put it here. Okay, and you realize that the eigenvalues will be equal to the natural frequency. So one of the natural frequencies, so we have 2 natural frequencies. So each one of the natural frequencies should correspond to one of the motions. So one of the motions is probably going to be both of these masses moving together, and the other frequency is going to correspond to each one of these masses moving away from each other. Okay, so now that we do this, we have 2 eigenvalues with 2 natural that correspond to natural frequency. To each eigenvalue, to each frequency, going to correspond an eigenvector that I think I call a moche. So we did case 1, when lambda equal to lambda 1 squared, you substitute into this equation, and you end up having the ratio of the deformation x2 over x1 equal to this, and for lambda 2 equal to this. Okay, right now it might look complicated, but this is pretty easy. So we find out that this one you see, so we start rewriting, but basically what's important here is what? Is that you see that if this is 1, I mean, this is positive, this is going to be positive. Okay, it's not that obvious here. So let's see what we stop here. So I'm going to rewrite it on the different form. So we stop right here, okay? So we probably have 1 page or less as what we need to show for the solution. So we did the first mode, the second mode. And this was page. So let's finish this, the theory quick, and do an example, and you will see that it's not that bad, okay? Page 99. It's really a lot more than page 99 because we did some other pages. So it should be page 1, 2, 3, 4, 5 here. This page 99, it doesn't matter. Oops, okay, I need to turn on this camera. Okay, so here in this solution, this value x1 1, x2, 1, x2, x1, 2, and x2, 2. All these are variables that need to be determined. Okay? So in order to determine those constant of integration, what do we need? Initial conditions. Okay? So basically it's the same process as before. All right, so we have these equations here, and now the only thing I'm going to say is that to solve for the constants x11, x12, x21, x12. Okay, so on top is the mode. Okay, yeah. So, all right. So to solve, and that's in green. So let's put it here where. Oops. So where the x 1, 1, x 1, 2, x 1, and x 2, 2 are constants of integration that are determined from initial conditions. Okay, so you need two initial conditions for the first equation, two initial conditions for the second equation, no? For each one of them. Okay, and let's say the final solution so what do we have? We had x of t, the assumed solution was what? Was this over here. So our solution at the end would be what? Would be x1 of t plus x2 of t, where each one of the solutions would be this equation here with after you solve for the constants of integrations. Okay? So let us do an example, very quick, and I think everything will be a little more clear. All right, so example. So on this example is the undamped, so we're going to have two masses. So basically we're going to do just like we did on the derivation, but we're just going to put values, okay? I'm not changing anything. So you have here K1, K2, K3, and this will be M1 and M2. So let's say this will be the origin for X1. This will be the origin for reference frame X2. Okay.
And here we're going to say no friction. No friction. All right, so we're going to have M1 equal to M, M2 equals to 2M, K1 equal K2 equal to K, and K3 equals to 2K. Okay, and here, this is just for the MATLAB code. On MATLAB code, I'm just going to say M equal K equal 1. This is just for MATLAB, okay? MATLAB code. It's not needed for derivation. But in MATLAB, you need to put values, okay? So, all right. So over here, if you have to do this, what you do, you will do the free body diagram, but to save some time, and then you will say the equation of motion will be of the form, so equation of motion this is what we just did, so I'm not going to recopy, but if you have this in an exam, what is the stuff I would like to see? Again, you don't need to do the whole derivation, but just do. So it's exactly the same problem as over here. You can do this figure without the dampings, no? Okay, without the force. And say from the figure, we get this equation of motion where this will be 0 and this will be 0, no? Okay? So if we do that, what we're going to get, the equation of motion will be equal to M 0, 0, 2M, which is will be M2. X double dot 1, X double dot 2. Plus now this matrix here is equal to 2K minus K minus K 3K. X1, X2. And this is equal to 0, 0. Okay? So again, if you think about it, this corresponds to what? M1, M2, no? We know M2 is 2M1, and here will be K1 plus K2, K2 plus K3 minus K2 minus K2. So K1 plus K2 will be what? 2K. This one will be what? K2 plus K3 will be 3K, and minus K2 will be minus K minus K, no? Okay, so basically substitution. So now, so to find solution, what will you do? You assume solution. So the form x of t equal x e I lambda t. Okay, so let's go into a bit more detail. So you come here, and now what can you say? You assume solution, you substitute, and I mean, let's just do it, okay? As practice, okay? That way we just redo, but we're going to follow exactly the same procedure. So this should be what? Minus, let's just do it. So what would that mean? Okay, let's do the first one in detail. This will mean that x double dot of t will be equal to x minus x lambda squared ei lambda t. All right, so substituting. into equation of motion, we should get one equation that will be similar to this one, no? Okay? We have here EI lambda T. So let's say, so we'll have here the 2K. Let's see if that's the same way I wrote it here. Okay, no, so let's start with this one. Okay, so you will get minus M for this term over here. Okay? Would be minus M lambda squared. All right, back over here. I mean, you can do it over here. Plus 2K. Then this one will be minus K minus K, and this one will be minus 2M lambda squared plus 3K. And now you have here X1, X2 of this should be equal to 0. Okay, so basically we follow the same procedure that we have over here. All right. So again, when is this equation satisfied? When this x1, x2, this term will be equal to 0. Or when this determinant will be equal to 0. So this will give us page 100. So the previous equation is satisfied if and only if what? X1 equal X2 equal to 0, which will be the trivial solution. Or when the determinant of minus M lambda squared plus 2K minus K minus K minus 2M lambda squared plus 3K will be equal to 0. And this corresponds again to this step over here. All right. Okay. So over here, let me pause for a second. All right, so let's see over here, example. 2 degree of freedom. So I guess it's still the same thing. We need to put this one here, I guess. I was under the impression if you put 2, it's going to do it bigger. No. All right. I want to do some text now. So generally, I always start my codes with clear all, CLC, not to clear the variables, clear the screen. And now let's see, on this problem, we say to use m equal to 1 and k equal to 1. All right. So what I'm going to do over here is rewrite these matrices, okay? The M matrix. So let's see, the M matrix will be given to as what? Let's call it capital M. So we have, oh, okay, so I'm going to have to change maybe notation here. We have, and then we add over here, M1 was equal to M. Then what else did we say? M2 will be equal to 2M. All right. And then we had K1 equal to K, K2 equal to K, and K3 equals to 2K. All right. That's from the problem statement, no? All right. So now what I'm going to do is write the matrix M over here. So we have over here M1 is 0. So this is the first row. And if you want, I can go to the next row. We have 0 and 2, no? If M is equal to that. Or we can just put actually the values, M2. Let's put the values, M2. Just this. And then we have the matrix K. That will be equal to what? So we just put the general K1 plus K2. This one will be minus K2. This one should be minus K2. And this one should be K2 plus K3. Okay, so now what we're going to do is solve eigen problem. All right, so basically we have vectors and eigenvalues. So there's two ways to do it. This is the way I generally do it. You have here the eigen, let's say eigen vectors, no, eigenvalues. No, eigenvectors is the command. And then we're gonna have eigen values, and this is going to be equal to the eigenvalue problem, which will command EIG of K M. All right, so we solve that. Let me save it here, maybe where I can give it to you later. Let's see. Okay, so let's say MATLAB, but this one, 2 degree of freedom, example 1, in case we do that. Save. And now if we run it, okay, it's giving us here some, you see, eigenvalues and eigenvectors. All right, so let's just copy to say that the eigenvectors, sorry, that the eigenvalues are come here. So let's say here from MATLAB code, we're gonna get that lambda 1 square, which is, we said a natural frequency 1 square is equal to 1, and that the second frequency is equal to, I think was 2.5. Okay, so now is where it comes a little bit different. So now we say that for each eigenvalues correspond an eigenvector. Okay, so let's write that down. but here you see the way they look like. All right, so I mean they're correct, but so now we said to each, so for each eigenvalue, which physically mean the natural frequency, so for each natural frequency, which is the eigenvalue, there is a corresponding eigenvector, which is what I call a mode shape. Okay, so for each frequency, natural frequency, there's a corresponding eigenvectors that should simulate what? The two types of motions that you can have. Either they move together or they move away from each other, no? Okay? So in MATLAB, now we look at the MATLAB on the output, this first, so this is the eigenvalue. Here, the first column corresponds to the eigenvector for this eigenvalue. And now this second column on the eigenvector corresponds to the eigenvector for this eigenvalue. Okay? So let's say, so for lambda 1 squared equal to 1, MATLAB give us what? Gives you the eigenvector. So the eigenvector for 1, let's say, will be this. Give us to be equal to, I think was negative 0.5774. Negative 0.5774. And the eigenvector 2, so this is a vector, and you put a bar on top, you don't have to, but is equal to what? Is equal to minus 8168 and 0.4082. Okay, so over here, when we went to the class notes over here, I know it looked very complicated, but what did I do over here? So we solve for each one of the cases, there's an eigenvectors, okay? That will be x2 over x1, and then I say, okay, what would be the first one? If you take this, you keep one constant and divide the other one by this one, you get an, I mean, it's normalization, no? Okay, so let me explain that, it might be just easier. So, now, let's say, let's rewrite these two eigenvectors, okay? But before that, let me put something in red. There are an infinite number of, I'm going to put here mode shapes, which is the eigenvectors for a specific natural frequency or eigenvalue. Okay, so by saying that, but this is important, guys, because this is an error that sometimes, I see many times in many engineers, and it's just a lack of understanding. So for this one, so for example, for lambda 1, squared equal to 1. This is the natural frequency of the eigenvectors. We have x1 here from the MATLAB code is equal to negative 0.5774. Negative 0.5774. Okay. Now, what happens if I divide both of these one by 0.5774? You will get, so this will be equivalent to minus 1, minus 1. Yeah? Or what could I do? I could divide this one by minus 0.5774, no? And this will give us what? 1, 1. Or what could I do? I could divide this by whatever you want. 2,533, no? And it will give us a specific another eigenvector. Okay? So now what is the physical meaning of these eigenvectors? We say that the eigenvectors, if you look from the class note, so this will be x1, this will be x2, no? So being in x1, x2 is, this is the motion of x1, this is the motion of x2. So basically what the eigenvector is saying is that if this is moving 1, the other one is also going to move a distance 1. Okay? If this one moves minus 1, this is going to move minus 1. If this one moves minus 0.5774, this one's going to move minus 0.5774. Okay? But guys, this just tells you what is going to be the behavior. But that doesn't tell you what is the distance that this is going to move. Do you understand this part? Because you see here you have multiple ones, no? They all have different values, but they all have the same behavior. Okay, they will show you basically what is this showing you is that this block, no matter what you do, will be moving together. If they move positive, they move positive. If they move negative, they move negative together, no? But this value here does not represent the distance. Okay? It's like to define the direction of a line, you have an infinite number of vectors, correct? Yeah? This is the same thing. The eigenvectors define the direction of a vector, but you have multiple vectors with different amplitudes, correct? Yeah? All right. So this is what we got. And now we're going to do the same thing for the second eigenvector. So for lambda 2 squared equal to 2.5, what is MATLAB giving us? We have here the code minus 0.865, 8165, and positive 4082. Okay, so this is the eigenvector of the mode shape. So what can we do over here with this one as well? Okay, let us divide both of them by 0.8165. What are you going to get? Minus 1. And really this one, if you pay attention, is actually half of this one, no? So what will you get? Minus 1, 1/2. But what could you have done? You could have divided by negative 0.8165, no? Both of them. Then what will you get? 1, negative 1/2. Or you could divide by any combination that you want. Okay? This answer here is as correct as this one or this one. What is the difference here? It's a different normalization, no? You normalize with a constant. Okay? So what is the meaning of this eigenvector? So this means at this natural frequency, omega 2 squared equal to 2.5, what should be the mode shape of the behavior? It means that when the first one is moving -1, the other mass will be moving 1/2, no? Or when this one is moving 1, this will be moving -1. So we go again to this figure here. That means that if this one moves -1 to the left, this one is going to move 1/2 to the right. Okay? Or let's say on the opposite direction, if this one moves 1 to the right, this one is going to move 1/2 to the left. Okay? All right? So that's basically what it means. All right, so if you want, let's do a figure or geometrical representation. I don't know if it's good or bad, but let's say geometrical representation for mode shapes, which is the eigenvectors. So let's say you have here x1, here you have x2. Again, I don't know how good this is to do it this way. I've seen it in many books, but here we put any values, but let's say we want to represent this one here, 1, 1. So when 1 is moving 1, the other mass will also be moving 1, no? So they will move in together. So this means both masses M1 and M2 move together. Now, if we use this one to represent x2, what would that give us? When this one is moving 1, M2 will be moving the opposite, no? So will be moving the opposite. So when M1 moves 1, M2 moves in the opposite direction, half the distance that the other one will move. Okay, so I don't know, if it's good or bad to represent it this way, but at least we can represent it, no? All right, so we studied the free vibration, so no force and undamped. Okay, so the next thing to do is to study what? The force damp vibration response. Okay. So in this case, it's the same figure as before. I'm not going to redo it, but you will have a damper, no? So basically, you will have this figure over here, all right, with F1 and F2, no? Okay, and the damping, C1, C2, C3. Here I'm going to change a bit the notation, it should be C11. Okay. So the most general form of the equation, so the most general form of the equation of motion will be what? Obviously it's going to be simplified, okay? But will be to have here M11, M12, M21, M22. So basically means to have values everywhere on the matrix. F1, F2. Sorry for that. At the end is F1, F2, okay? But again, most of the time, this matrix is going to be symmetric, so the M12, M21 will be 0. Okay, so again, if you have this equation, what is the procedure? One, assume solution. What happens is that I do the general solution with the most general case, okay? Now, so assume solution. What will be the assumed solution? If I use index notation, x of j equal to capital xj e I omega t. Well, what is the capital omega? This time is not the natural frequency. This is the forced frequency, no? Okay. So this is equivalent to what? We're assuming x1 equal to capital X1 EI omega t, and this is equivalent to x2 equal to capital X2 EI or capital omega t, where omega here is the force frequency. Okay, what is the second step on the procedure? You substitute the assumed solution into equation of motion. All the time the same thing. All right, if you do that, you're gonna get the equation AI omega t, and then you're gonna get here, hopefully I have space, minus M11 capital omega square plus IC11 omega plus K11 minus M12 capital omega square plus IC12 omega plus K12, and basically something similar on the other side, so it will be minus M12, oops, so at the bottom was, yeah, it would be 2-1 here, but since it would be equal, doesn't matter, 1-2 omega square plus IC12 omega plus K12. It should be K21 really here, but they're gonna be symmetric. Don't worry, they're always gonna be symmetric. Minus M22 omega square plus IC22 omega plus K22. x1, x2, and this should be equal to the EI omega t F1, F2 of the forces. So why do we assume the solution using the force frequency? Because at this step, what can you do? You can cancel these two terms. Okay, so now we go to notation. So be careful here. So using impedance notation. So guys, you see here the notation is becoming complicated, but the process is the same over and over, no? So what is the impedance notation? It's just saying that we're going to call this Z RS of I omega. So for example, this expression here, okay? We can write it as minus M RS lambda squared plus IC RS for this one, omega plus K RS. So basically, if R and S equal 1, we have this expression here. Yeah. If R equal 1, S equal 2, you have these expressions over here. And if R and S equal 2, you will have this one over here. Okay. So this is going to help us not to have to rewrite this every single time with a single indexes. Okay. Or this, you can show that this is also equal to what? M RS omega, so this time is the natural frequency RS. And this is the same thing as we did with 1 degree of freedom. This will be equal to 1 minus the ratio of the force frequency to the natural frequency RS square. This is a square. Plus I 2 damping RS of the ratio of the frequencies. Okay, so in this equation here, oops, I should have done that in red. So in this equation here, RS will be either equal to 1 or to 2. Okay, so using this notation here, we can rewrite the above equation. Okay, so I have to rewrite it, which I'm not too happy about it, but so then oops, the expression I'm just going to recopy this one here. okay, but without the exponential function. We have minus m1 lambda squared plus IC11 omega plus K11 minus m12 lambda squared plus IC12 plus K12 minus m12 omega squared plus IC12 plus K12 minus m22 omega squared plus IC22 plus K22 of x1, x2 will be equal to f1, f2. Okay, so with the impedance notation, we can rewrite this as what? As Z of I omega and this is will be this matrix over here, okay, where R and S will be 1 and 2 of what? Sorry, of X. So will be this X should be equal to F. That will be F1, F2. If you want to compare here vector and vector. So these two expressions are equivalent. Okay, it just helps a lot on the writing. We want to compare here Z, RS, and RS will be equal to 1 and 2, okay? And this could be R and R if you want, but it's not needed. Okay, so from which what would you have? The solution X, if we solve for X, should be equal to what? Should be equal to the inverse of Zi omega. So you solve for X, you multiply by the inverse of this one on both sides, so this one disappears. And here you're gonna have F. Maybe remove here the R and the S because I'm just thinking that I'm just making it redundant because if I put here the bar of the vector, that means that this is a vector, no? Of two quantities. And this is the same thing for the fourth. You want to keep the R, don't put then that this is a bracket. But it's fine. Either one should work. Okay, so now Z is this expression for a 2 by 2. You might remember or not remember. What will be the inverse of this matrix over here? So for a 2 by 2, it's pretty simple. This is equal to 1 divided by the determinant. So this would be Z11 I omega times Z22 I omega minus Z12 square I omega, which is the determinant of this matrix. And then here, generally you just flip the order and change the sign in one of them. But again, don't worry about this because you'll all be doing this with MATLAB. So you switch the sign, either on this color or this color, Z11 I omega. Okay, let me write one last thing, because now we have the solution for x1 and x2, okay, which is from the assumed solution. We know the false frequency, we need to find these values for x1 and x2, no? So we can find it from this equation here, knowing that this is equal to this, you substitute by the force. This will give you that, and I will stop over here. X1 will be equal to F1 Z22 I capital omega minus F2 Z12 I capital omega divided again by the determinant Z11 I omega Z22 I omega minus Z12 square I omega, and X2 will be equal to minus F1 Z12 I omega plus F2 Z11 I omega divided by the determinant Z11 I omega Z22 I omega minus Z12 square I omega. Okay, so finally, solution is obtained by substituting those two solutions into the assumed solution that was what? X of j was equal to capital X of j ei capital omega t. So guys, again, I know the notation changed, but the procedure remained the same, no? Okay, what happened is that since we moved to 2 degrees of freedom, it's not only one line. You remember the notation was already cumbersome with 1 degree of freedom, imagine with 2, no? So we use that notation, the ZRS. Okay, so next time we do an example, and you will see the examples when you start putting numerical values, it goes a lot faster, okay? And we can use MATLAB as well.